next talk is actually a tutorial being given by Adra. Hi, Adra. So I make you co-host just to be sure that you are able to share your screen. So Adra is a research scientist at Apple. Adra and I met back at UMich. She's a brilliant researcher, and she has worked in several universities. So she has worked as a postdoctoral at the Boston University, as well as at Northeastern. And before that, she was at the University of Michigan in the Department of Mathematics. She has done a lot of very interesting work. She has done work in testing differential privacy. And today she's going to talk about a really interesting and nascent area about privacy amplification. So without further ado, I'll leave you the floor.
Sure. Hi, everyone. Thanks for coming. So as Andrew said, I'm Audrey McMillan. I'm currently at Apple. And today we'll be talking about privacy amplification. So this is a tutorial, so it is an hour-and-a-half long. So what that means is that I would like, if possible, any interaction. So feel free to interrupt, ask questions. An hour-and-a-half is a long time to listen to someone else speak. So feel free to jump in. And always in a talk, you want people to learn something, but in particular in a tutorial, it feels egregious if no one learns anything. So if you are confused or if I'm going too fast, feel free to slow me down. We really don't need to get to the end of the talk. There's particularly a section at the end that if we don't get there, that's fine. So don't worry about slowing it down. I'm happy to answer any questions you have. Do I need to go into like present mode? Yes. Okay, so I'm going to talk about privacy amplification, specifically in differential privacy. So our goal throughout this talk is going to be to explore how privacy amplification results can be used to improve privacy guarantees. So we're going to be talking about three specific types of privacy amplification by subsampling, by shuffling, and by diffusion or post-processing. Okay, so all of these techniques come with their own kind of privacy models, some assumptions you need to make. We'll talk about the pros and cons of those models. And throughout the talk, I'm going to use stochastic gradient descent as my example of a mechanism that I can analyze using all of these different techniques. And we'll see some trade-offs we need to make to improve the privacy guarantee of stochastic gradient descent, which in turn, of course, improves the utility guarantee. Oh, and the last thing I want to note is that I'm not going to assume any knowledge of differential privacy. The talk is going to kind of ramp up, but I will hopefully be introducing everything. If you are familiar with differential privacy and the differential privacy literature, a lot of what I'm going to be talking about is going to be prior work. But around the middle of the talk, around the half-hour, 40-minute one spot, I'm going to be talking about a new result on privacy amplification by shuffling. So if you zone out, make sure to jump back in for that bit. I think it's a really nice new proof on that. Okay, so let's first talk about what differential privacy is. So suppose you're a data analyst and you have a database and you want to compute some function on your database. So our function is f. So if you are a data analyst that cares about privacy, your goal is twofold. You want to compute your function or something that looks like your function, but you also want to protect the privacy of your data subjects. And protecting the privacy of your data subjects is kind of a nebulous term here. And so one of the key contributions of this seminal differential privacy work by Dwork, McSherry, Nissim, and Smith was to formalize what we mean by protecting privacy. Okay, so let's see what they meant. Okay, so suppose I have my database P. And now imagine I have another database P prime that differs from P in only one data point. So this green data point has turned pink in P prime. Now imagine running a mechanism A on P versus P prime. Then we're going to say that this mechanism A protects the privacy of P if from the output of P, it's impossible to confidently guess whether the input was P or P prime. Okay, And this protects the privacy of this individual because we can't tell whether their data was green or pink. Okay, so what does it mean to not be able to confidently guess whether the input was P or P prime? So we're going to use a notion of closeness between random variables. So I'm going to say two random variables are epsilon delta indistinguishable if for all events in the output space, the probability of seeing that event if you're sampling from X is about the same as the probability of seeing that event if you're sampling from X prime. So think of epsilon here as pretty small, say like 0.1-ish, and delta as say 10 to the negative 6-ish, very small. So what this inequality is really saying is that these two probabilities have to be close. And so this is a formalization of this statement we said before. So if I get a sample from X or X prime, it's impossible to confidently guess which one it came from because that output was almost as likely under both of them. Okay, so back to our databases. So we have P and P prime. And we're going to say an algorithm A that goes from the set of databases of size n into some output space is epsilon delta differentially private if for all possible pairs of neighboring data sets, so all pairs of differing data sets that differ on the number of a single individual, the output distributions, A of P and A of P prime, are epsilon delta indistinguishable. So what this says is I can't tell which one I was sampling from, so I can't tell whether the input was P or P prime. Okay, so that's what we mean by privacy. And of course, our hope is that we can design an algorithm, A of A, so that A of P is close to F of P, which is the function we actually wanted to compute. So a large amount of the differential privacy literature is on designing algorithms A that are close to functions that we want to compute, but also satisfy differential privacy. And the reason why this is possible, of course, is that typically we care about population-level statistics. So we don't really care about the specific data set itself. We care about kind of the population it came from. And if you care about population-level statistics, then no single individual should change your statistic that much. It shouldn't be having that much of an impact. So we can often design differentially private algorithms that actually emulate the thing we're trying to compute really well. Okay, so the model of differential privacy I just defined is actually called central differential privacy. And so I only cared about the output of my mechanism being differentially private. So I assumed that I could collect all of my data points together in some central server, and then I only cared about the privacy of the output of that central server. There's an alternate model called the local model. And in the local model, I don't assume I have this central server. So my data analyst and my central server are the same person here. And I don't necessarily trust them to collect all the data together. So each of my data subjects is going to want to privatize their data before it gets to the central server. Again, this is a more popular notion in practice for a couple of reasons. So it's a stronger privacy notion. It's also easier to build systems that satisfy this. I don't have to be as worried about the security of this channel from my data subjects to my central server. It's also often true in practice that the data analyst and the central server are kind of the same person. This person collecting data is the same person as the person computing something on the data. And the local model also allows us to do interactive protocols. So I don't have to have everyone send their data all at once. I can have them interact with the central server in this way. Okay, so I need kind of a different notion of privacy for this, very similar. So now instead of having a database, I have a single data point. And I have X and X prime, green or pink. And I'm going to say an algorithm A that maps from my data universe into any space is an epsilon delta local randomizer if for all possible pairs of data points, X and X prime, the output distributions A of X and A of X prime are epsilon delta indistinguishable. So you can't tell whether the sample was X or X prime. Okay, and again, my hope is that I can collect all of these local reports together, perform some post-processing function, and get something that's close to the function that I actually wanted to compute. Okay, any questions about the definition of differential privacy? So we're only going to really talk about two differentially private mechanisms throughout this entire talk. So one of them is the Gaussian mechanism, which I'll talk about now. And a little later, we're going to talk about something called binary randomized response in maybe 45 minutes. Okay, so the first one we're going to talk about is the Gaussian mechanism. So suppose I have my function that I wanted to compute, and I have the additional property that my function doesn't vary very much on neighboring data sets. So if I have any pair of neighboring data sets, P and P prime, the L2 norm of the difference between F on these data sets is less than 1. Then I can define this mechanism called the Gaussian mechanism that computes F of P and then adds Gaussian noise. Okay, and this can be in any dimension here. So y has to be r to the d. Okay, and then this algorithm satisfies this privacy guarantee. So this is my epsilon delta guarantee here. So it's square root log 1 over delta over sigma delta differentially private. Okay, and this is essentially coming from the fact that two Gaussians, if I have two Gaussians that means are close, then they satisfy this indistinguishability condition. Okay, so for a lot of the talk, we're only going to be dealing with this differentially private mechanism. All right, so as our introduction to differential privacy. So the other kind of component of this talk is going to be empirical risk minimization. So we're going to use this as our motivation. So in empirical risk minimization, I have some distribution Q over my data universe, and some convex set K, and some loss function. And what I'm trying to do is compute the element of my convex set that minimizes the expected loss of my loss function over the distribution Q. Okay, and empirical risk minimization is really a workhorse of machine learning. It happens everywhere. So this is a really important algorithm to be able to analyze properly. Okay, and of course, how do we solve this? So we don't have access to the distribution Q itself. What we have access to typically is samples from Q. So I'm going to assume that I have n samples from Q. And what I do is compute the minimizer of the empirical mean of the samples that I'm given. And of course, this empirical mean is an estimator to this expectation. Okay, but how do I compute this minimum? So this is where stochastic gradient descent comes in. So I'm sure a lot of you are familiar with stochastic gradient descent. We're going to be using a very vanilla form of stochastic gradient descent throughout this talk. But of course, there are more complicated versions. And in fact, if you want to optimize these methods, you do need to use the more complicated notions. But that's not the purpose of this talk. So we're going to stay on this kind of vanilla version. Okay, so what it does is we're going to call the WIs our iterates. So we initialize our estimate for the min. So we're going to initialize it at 0 here. And then we're going to iterate over our data set. And at each step, we're going to do the following. So we're going to take the gradient of this function f at the current iterate and the current data point x1. And then we're going to move, so that moving to our picture on the left. Can you see my arrow, my little arrow guy? Yes, okay, cool. Okay, so then what this does is it's going to move the current iterate in the direction of the gradient, and that should be downwards. So we're going to assume that f is convex, and so this moves us towards the minimum. Okay, and if we ever fall outside of our convex set K, then we just project ourselves back into it. Okay, so we run over the entire data set, and then at the end.
No, I cannot see the mouse, the arrow mouse.
Oh, you can't see the mouse. Okay, I will keep that in mind. Okay, so we iterate over our entire data set, and then at the end, we're going to output the last iterate, Wn. Okay, so of course, this thing isn't differentially private. We're not doing any randomness. But notice that the data sets only appear in these gradient terms here. So this is the only place they appear. And so I want to create a differentially private version of stochastic gradient descent. And the particular variant we're going to use was introduced in a series of papers by Chaudhuri-san and Sawati and Vasily Smith and Thakurta in 2013 and 2014. And so what they proposed we do, well, sorry first, do one more thing. So this is going to be impossible to do if any single data point can totally derail the answer. So I really have to bound the impact that any one data point can have on my answer. And one way to bound that impact is to bound the gradients themselves. So I'm going to say all of my gradients are bounded in L2 norm by 1. And 1 is not important here. I just don't have to carry around another constant. Okay, so I'm going to assume it's bounded by 1. And so now I can use the Gaussian mechanism on these gradients. Okay, so all I'm going to do is each person is going to, when they report their gradient, they're going to add Gaussian noise to it. And now each of these steps is differentially private. And essentially what this does is it just perturbs this gradient a little bit. And hopefully we're still moving in the right direction. Okay, so the goal throughout this talk, kind of overarching theme, is going to be analyzing this mechanism. And we're going to introduce hopefully a lot of interesting ideas in the process of doing that. But we're going to keep coming back to this mechanism and how to analyze it. What we're going to do is keep track of the privacy guarantee. And what that actually does is if we have tied up privacy guarantees, that allows us to set sigma smaller and smaller. And we want to set sigma as small as possible to get the best utility guarantee. Okay, but I'm going to phrase it in terms of doing the privacy, tracking the privacy. Okay, so let's give our first analysis. This is our most naive analysis, but also what we're going to talk about has a lot of benefits. Okay, so notice that because I'm iterating over the data once, what I'm actually running is a locally differentially private protocol that is just an interactive mechanism between my central server and my data subjects. So I send the first data subject W0, they send back their noisy gradient, I do something on the server, I send W1 to the second person, they send back the noisy gradient, etc. Okay, and I only interact with each person once. So this really is a local DP, a one-pass local DP protocol. Okay, so I can use that to analyze it. So I know from the Gaussian mechanism that each person's local report is epsilon delta dp for this epsilon here. When we talked about 4 square root 1 over delta over sigma. Okay, and because I only interact with each person once, this just implies that the entire mechanism is epsilon delta dp for the same epsilon in the central level. Okay, so this is my first analysis. Any questions here? Good. Okay. All right, so I'm going to keep track of all our analyses in this table. So we filled in our first row here, our most naive analysis. Okay, so notice this doesn't depend on n. The guarantee is the same. Yeah.
Sorry, Adra. We actually have a question from the audience. So Borja asked, doesn't eta affect the analysis?
No, it doesn't. So it is important when you want to optimize this for the utility, you do need to set eta carefully, but doesn't actually, it's not going to affect any of our privacy analyses. And that is largely because, so if for this particular analysis, if I look at what I'm relying on for the privacy, I'm just relying on the fact that these noisy gradients are private, and eta is only something that kind of exists on the central server. So it doesn't matter for my privacy guarantee. It does matter for my utility, though. That's an important point. Okay. So I'm going to keep track of our privacy guarantee. Obviously, this is our most important thing. I'm also going to keep track of 2 other things. So this is whether my algorithm allows me to release the noisy gradients, and also whether it allows me to release the order of the samples or who I'm interacting with. And these are important for different reasons. Yeah.
There's a follow-up question. So Mohammed asked, are we bound norm 2 of GRODs?
Are we what, sorry?
Are we bound norm 2 of the grid? So are the gradients bound in the norm 2?
Yeah, so all throughout, I'm going to assume that my gradients are bounded by 1 and norm 2. I am going to drop constants pretty willy-nilly. And I do apologize for that. So there actually should be like a square root 2 in front of this epsilon. And this is just because these constants are kind of annoying to keep around. I do promise that none of them are very big. So they're all kind of square root 2, that kind of order. But I am going to drop them quite often. So most of the time, all that's important is that I'm bounding things by constants.
Perfect. Thank you, Audra.
Okay, so these two things are important for different reasons, and they're both really helpful to have. So this first one, whether I can release the noisy gradients. So this is important for a couple of reasons. So the first one is that if I can release the noisy gradients, then I can release all of these iterates. And if you're familiar with stochastic gradient descent, you might have noticed that typically what you do is not release the last iterate. The last iterate actually doesn't have very good utility guarantee. Typically what you do is you'll average over some subset of the final iterates. Or have a random stopping time, you'll do something because the average iterate has good utility, but the actual last one itself doesn't have particularly good utility. But if you can't release the noisy gradients, then you really can't utilize that. Additionally, these gradients give us a lot of information about what the mechanism is doing. So in particular, we can get an idea of whether we actually are converging if we can look at these noisy gradients. Okay, so that's a good thing to have. The second thing, whether it releases the order of the samples, is useful for a different reason. So remember I said that the local model was a more desirable model for lots of reasons. And one of them was that it's easier to build systems that satisfy this model because you don't have to worry about the sensitive data living anywhere or being commuted anyway. So if I'm not allowed to know, if the central server, my privacy guarantee, relies on me not knowing who I'm interacting with, which is going to happen for a few of our algorithms, then I have to build some way of doing that into my system. So I have to have some kind of intermediary between my data analyst and my subjects so that the data analyst doesn't know who they're interacting with. And that can just be an architectural problem. These systems can be built, and in fact, they are being built, but it is a slightly harder system to build. Okay, so the remainder of the talk is going to work like this. So I have 3 privacy amplification techniques that we're going to talk about. So if each one is kind of its own model, so I'm going to define the model. I'm going to give some intuition for why that technique amplifies privacy. And then we're going to always jump back to gradient descent and think about how that technique can be used to analyze gradient descent. Okay. Any more questions at this point? I don't think I can see the chat.
I will try to interrupt you. I'll try to be rude and interrupt you.
That sounds great. Okay. All right, so we have 3 techniques: amplification by subsampling, amplification by shuffling, and amplification by diffusion or post-processing. Before I talk about any of those, I just want to establish one notational thing that I'm going to use a lot. So I'm going to use this notation. So y, x, and x prime are random variables. And so if I say that y is the sum of a convex combination of x and x prime, all that means is that y samples from x with probability 1 minus alpha and x prime with probability alpha. Okay. All right, so I'm going to start with subsampling. Okay, so we're back in the central model. So in the central model, all my data subjects send their data to the central server, who then does something and sends the privatized version of their answer to the data analyst. So now imagine that a random subset of the subjects provide their data. And it's important here that this is a random subset, and this subset is not known to the data analyst. And the question of privacy amplification by subsampling is how much more private is this composition? So do these people get any extra amplification, any extra privacy from the fact that I don't really know if they're in the sample or not? And of course, the answer is going to be yes, they do. Okay, so to the best of my knowledge, the first place that the subsampling amplification was noticed was actually a blog post by Adam Smith. And then it appeared in this Cleaners paper in 2010. And there's a really nice treatment of it in this Balibarth and Gabordi paper, who kind of give a general treatment of subsampling mechanisms and how one analyzes the privacy of these mechanisms. Okay, so we're going to talk about 3 types of subsampling: Poisson sampling, sampling with replacement, and sampling without replacement. Okay, so in all of them, I have my server and I have my data subjects. So in Poisson sampling, all of my data subjects flip a coin that's heads with probability gamma. And if they get heads, then they send their data to the server. Remember, it needs to be kept secret who sends their data to the server. In sampling with replacement, my server picks a subset of size m, but they can choose people multiple times. So think of this as each time they pick a single person, and they pick a single person m times. And whoever they choose sends their data. Again, the subset needs to be kept secret. Okay, my final one, sampling without replacement. The server just picks a subset of size m from the data set and sends their data. So no one sends their data twice here. Okay, and then the server runs an epsilon differentially private protocol. And my question is, how much more private is the composition of the sampling with the epsilon DP protocol? Okay, and the answer can be quite a lot. So what happens? So let's look at Poisson sampling first. So the amplification or the privacy of the total mechanism is gamma epsilon for small epsilon. So there is a bound for large epsilon, but it looks quite different to this. So we're going to focus on small epsilon. Okay, so what this says is you get amplification by about the fraction of the people who contribute their data. And the same thing happens for sampling with replacement. This one's a little bit more complicated. I also need the fraction of people contributing their data to be quite small. So n here is the size of my data set. And so I get about the fraction of people contributing their data times epsilon as my privacy guarantee. And the same for sampling without replacement. I also get m over n times epsilon. Okay, I can do the same thing for epsilon delta differential privacy.
Yeah, just a question. When you say for small epsilons, you mean epsilon less than 1?
Yeah, so what this actually appears as is the real bound is like e to the epsilon minus 1 times gamma, say. And so e to the epsilon minus 1 is about epsilon for smallish epsilon, but for large epsilon, it's obviously not.
Okay.
Right. So that's what so there is a bound for large epsilon, it's just not very meaningful.
Perfect, thank you.
Okay, so I can say a similar thing for epsilon delta differential privacy, so it also amplifies. The amplification bounds for Poisson sampling and sampling with replacement do exist, but they're just quite hard to state, so I'm not going to state them here, but if you are interested, then you should see this very nice paper. But the one for without replacement we can state quite easily, and so it just says you get about the same amplification in epsilon as you got in the pure different privacy case. And you also multiply delta by also about the fraction of, say, people who are in the final sample. Okay. So this is privacy amplification by subsampling. So let's talk a little bit about why this amplifies privacy. Okay, so I have my two data sets, P and P prime, and now I have Alice. So Alice's data is different in P as it is in P prime. She's kind of the distinguishing feature. So the intuition is Alice is only in the sample with probability m over n. So I'm going to be doing the proof for sampling without replacement and in pure differential privacy. So pure differential privacy is just when delta is 0. It's a little easier to work with because our kind of the guarantee gives us a kind of strict bound on the probability density functions, which is nice to work with. Okay, so with probability m over n, Alice is in the sample. And if she's not in the sample, then the distribution is the same for P and P prime because she's the only part of it that's the data sets that is different. Okay, so let's formalize this a little bit. So suppose I have my algorithm A, my differentially private algorithm. I have my sampling mechanism that takes data sets of size n to data sets of size m. So this is randomized. And what I care about is the privacy guarantee of the composition of these two mechanisms. Okay, so note that I can decompose this on input P as 1 minus m over n times the conditional distribution of Alice not being in the sample. This is the probability that she's not in the sample, plus m over n times the conditional distribution if she is in the sample. And I can do the same thing for p prime. And now notice that these first two distributions are the same. When she is not in the sample, p and p prime are identical. And of course, when she is in the sample, it's slightly different. Okay, so now I want to analyze this, and I can actually appeal to a kind of more general lemma about indistinguishability. So I have two distributions, y and y prime, and both of them sample from the same distribution x0 with probability 1 minus gamma. So with probability 1 minus gamma, they're the same. And with probability gamma, they are different. So what this lemma says, and actually the lemma in the paper is a little bit more general than this, but this is the version we need. It says that if x1 and x1 prime are epsilon indistinguishable, so if when they sample from different distributions, their different distributions are not that different, and x1 and x0 are also similar or indistinguishable, then I get amplification. So y and y prime are gamma epsilon indistinguishable. Okay, so I took three mechanisms that were epsilon indistinguishable, and I turned them into a mechanism that was gamma epsilon indistinguishable. And again, this is only for small epsilon. Okay, so returning to our proof sketch. So now these two mixtures look like the mixtures I just had in my lemma. And I need to establish these indistinguishability relationships. So I'm not going to establish them formally, but let's talk about intuitively why they're true. So let's first look at the distribution on P when Alice is not in the sample, and the distribution on P when Alice is in the sample. So I can turn a sample that doesn't contain Alice into a sample that does contain Alice just by substituting her in for a random person. Okay. And those two samples are only differ on one person, so they're neighbors. And so the fact that A is epsilon differentially private implies that those two things are epsilon indistinguishable, or A on those two samples is epsilon indistinguishable. And that implies that these two mechanisms are epsilon indistinguishable. Okay, so that was a little bit vague or a high level. Does anyone have any questions about that? Does it seem true? Okay. All right, so now I can say a similar thing for the distribution over P when Alice is in the sample and P prime when Alice is in the sample. So I can just get from one sample, I can get a sample. If I take a sample of P of size M that contains Alice, then I can turn that into a sample from P prime that contains Alice just by changing Alice's data. So that is, again, just a change of one person's data. So the fact that A is epsilon dp implies that those two distributions are epsilon indistinguishable, which implies that these two conditional distributions are epsilon indistinguishable. Okay, so now we're in the exact situation of the lemma we just had. So we can say that these mixtures are m over n epsilon indistinguishable. Okay, and this implies that A composed with S is m over n epsilon differentially private, because there was nothing special about P and P prime. They were just a pair of neighboring data sets. So this is true for any pair of neighboring data sets. Sorry, forgot to get rid of the animation here. But what we have is that we've established this column here for pure DP, sampling without replacement. We got the bound that we wanted. The proofs of the other ones are kind of similar ideas. Okay. Questions about privacy amplification by subsampling? Great. Okay. So we're going to do what I promised, which is jump back to stochastic gradient descent and say how this amplification theorem allows us to get a better analysis of stochastic gradient descent. Okay. change my mechanism just a little bit. So instead of iterating over my entire data set, kind of from 1 to n, like I did before, what I'm going to do at each step is I'm going to sample a random point from my data set. Okay? And then I'm going to use that point to do my step or my iterate update. Okay, so this is a little different. I can, in particular, interact with the same person multiple times in this mechanism. Some people won't be interacted with at all. But on average, I'm going to kind of interact with each person once. Okay, but this mechanism is no longer locally differentially private because I can interact with people multiple times. So I'm going to look at it this way. So for each individual step, it's composed of a subsampling step where I sample just a single person from the data set with an epsilon delta dp mechanism where epsilon delta is this square root log 1 over delta over sigma delta, just from the Gaussian mechanism. Okay, and this is exactly what we just analyzed. So the subsampling amplification says that this step is actually, in the central model, square root log 1 over delta over n sigma delta differentially private. Okay, and this n comes from the fact that m, what we called m before, is now 1, because I'm just sampling one person. Okay, so I have that each step is epsilon 0 delta 0 differentially private, and I have n steps. And so now I'm going to pull a theorem out of my back pocket, which is the composition of differentially private mechanisms. So this is a general theorem, a workhorse of differentially private analysis, is that if you have n differentially private mechanisms that are all epsilon 0 delta 0 dp, then the composition of them is epsilon 0 square root n log 1 over delta dp. Delta n here as well. Okay. So now, if I substitute in epsilon 0 and delta 0 in here, I get this privacy guarantee here. So log 1 over delta over sigma n, over sigma square root n. Okay. So this becomes interesting when we compare it to what we had previously. So our first analysis didn't have any dependence on n, and now we've improved it significantly. So we've gone from having no denominator here to having a square root n in the denominator. So this is a big improvement. But what did it cost us? So we can still release noisy gradients. That was fine. But we can't release the order that we're interacting with the samples, or who we're interacting with, or how many times we're interacting with them. None of that is allowed to be known to the data analyst, and because that would violate our privacy guarantee, which relied on the fact that our subsample wasn't known. Okay, so this just means that we have to build in extra architecture in our system. We have to kind of protect that information. We also have lost our local DP guarantee in this new mechanism, because we can interact with people more than once. So this is no longer a local DP mechanism for this small epsilon delta anymore. Okay, so this is our first analysis. So we paid a little bit in kind of setting up an annoying architecture, but we also gained a lot. Okay, so our next amplification guarantee or system is shuffling. Okay, so remember we had the central model of differential privacy where we cared about what came out of the server. We had the local model of differential privacy where each person already had privatized their data by the time we got to the central server. And the shuffle model is sort of a hybrid between them. So it's a specific way of building in a buffer between the data subjects and the central server. And this buffer is called a shuffler. And it does kind of as advertised, or it's well named. It takes in all of the local reports and permutes them and sends the permutation to the central server. So you can think about this as anonymizing the local reports or breaking the connection between who sent the report and the report itself.
After we have a question from Borja. So he asked why, so referring to the previous mechanism, why is not local differentially private?
Yeah, so it's not locally different. So yeah, so if we look up at this algorithm, so the algorithm's in the corner, because I can sample, so each time I'm sampling a new person, and I'm sampling essentially from the same class of people each time. So I can interact with one person multiple times because they can just happen to have been sampled at multiple steps. And so because of that, if I can interact with you multiple times, then each time I interact with you, I pay some privacy. So it is sort of still locally differentially private, but for a much higher epsilon than the original mechanism was.
Perfect. Thank you.
Okay. Okay, so I have my shuffler. So my shuffler permutes the local reports and sends them to the central server. And the question of privacy amplification by shuffling is, if each person is already sending a epsilon differentially private local report, how much more private is the output of the shuffler? Okay, so this should intuitively buy me something. I'm anonymizing my data. So the question is, how much is it buying me? And the observation that it does actually buy you something was established in a series of papers in 2019. So this Chow et al. Paper looked at if each subject is running a binary randomized response mechanism. And this Erlingson et al. Paper proved a more general result, that whenever you have any locally differentially private mechanism, the guarantee after the shuffler is higher. So you get more privacy after the shuffling. Okay, and just like in local DP, I can have interactive mechanisms in the shuffle model. But remember, it's important that the central server doesn't know who it's interacting with. So it gets a sample at each time step, but it doesn't know who it came from. Okay. All right. So this is the shuffle model. Questions welcome, but I won't pause unless there are questions. Okay, so what this Erlingson et al. Paper showed is that the output of the shuffler, so if I look at this output in the central model, is this private. So if all the mechanisms are epsilon 0 dp, then the output is epsilon delta dp, where this formula here gives me the epsilon. And this is actually really important in both the low epsilon naught regime and the high epsilon naught regime. So the bound I'm giving here, the second kind of approximate bound, is only for small epsilon naught. But we get this kind of epsilon naught divided by square root n. But this model is actually also really important in the high epsilon naught regime. And this is because if I care about this central guarantee, suppose I'm going for a target central guarantee of, say, 0.1, then what I need to set my local guarantees to be is about like square root n. I can set them as big as that, and I still get a reasonable central guarantee. So in this model, I do care about having local DP mechanisms that have quite high epsilons. Okay, but I am going to sweep that under the rug for the moment, and we're just going to continue focusing on the low epsilon naught regime. Okay, so I get an amplification of about 1 over square root n. I'm going to mention this other paper conveniently by myself and my collaborators at Apple, where we took this number, this 3, down to 0.5. I mentioned this partly because it's my own work, but also because this is the proof we're going to talk about is the proof from this paper. There's a series of nice works in this area now. So I want to point to some of them here. So this Chow et al. Was concurrent with the Erlingson et al. That I just mentioned. Also independently established that shuffling amplifies privacy. And these other papers are follow-up papers that improve in various ways the analyses. Okay. So this is the shuffle model. And I'm actually going to spend quite a bit of time on this proof because I think it's a nice proof. And there are a few little tricks additionally along the way here that I think will be informative. Again, this is supposed to be a tutorial talk, so hoping you take like a few little tricks away from this, as well as kind of the overarching idea of privacy amplification. All right, so I'm going to introduce now our second differentially private mechanism, which is binary randomized response. Binary randomized response is actually really old. It's much older than differential privacy. I think it first appeared in like the 60s as a disclosure method. Okay, but it's quite simple. So all it is a mechanism from 0, 1 to 0, 1. And on the input 0, you output 0 with slightly higher probability than you output 1. And slightly higher is given by these probabilities here. So this is the biggest probability I can assign to 0 so that I can maintain differential privacy. Okay, and on 1, I do the opposite. I give more weight to 1, obviously. Okay. So I'm going to simplify the problem a little bit. So the actual bounds hold for interactive protocols and approximate differential privacy, but we're going to bring it back down to non-interactive protocols and pure differential privacy. So each person I'm going to have one local randomizer, A. Each person is going to send a report using this local randomizer, and then the shuffler is going to shuffle them and send the shuffles to the central server. And A is going to be epsilon differentially private, so pure differentially private. The proof actually isn't very much more complicated if I get rid of the requirement that everyone sends the same thing and I allow interaction. But just for brevity, I'm going to keep it to the simple one. And the proof of approximate is a little bit more complicated, but there's sort of a nice trick that gets you between them. Okay, so this is what we want to analyze. We're going to narrow down to 2 data sets, P and P prime. Remember, all we want to prove is that what the central server sees, which is the mixture, which is the permutation of all the local reports, is epsilon differentially private. Okay. So my notice that P and P prime differ on the first data point. The fact that it's the first data point is not important. That is, again, just for notational convenience. Okay. So how this proof is going to work is via reduction to a simple non-interactive protocol. So this non-interactive seems a little uninteresting in this case because we already established that we have non-interactive protocol. But in the more general proof, it is important that this is non-interactive. But also, it's just much more, it's going to be simpler than the protocol that we started with. Okay, so what this non-interactive protocol is going to do is on the first data point, so this is the data point that differs between P and P prime, it's going to run a randomized response. So it's going to output 1 with slightly higher probability on x1 and 1 prime with slightly higher probability on x1 prime. What everyone else is going to do is with some probability they're going to output 1, with some probability they're going to output 1 prime, and with some probability they're going to output this third symbol, which we're going to use theta. Okay, so everyone's going to do that. They're going to send whatever they sampled to the shuffler. The shuffler is going to shuffle them and send them to the central server. And what we're going to guarantee is that there exists some post-processing function G that can do the following. So it takes in what was given to the shuffler, what was given to the central server, so the output of the shuffler, and it takes in both P and P prime. So it doesn't know whether the sample came from P or P prime. It's just told both of those data sets. And the guarantee is that when I do this post-processing, I get the output, which is identical to what I would have gotten if I actually ran the mechanism I wanted on either P or P prime, depending on which one I input into this mechanism. Okay, so this is a reduction. So why is this a nice reduction? So there's something called the post-processing inequality in differential privacy. What the post-processing inequality says is that if you have an epsilon differentially private mechanism, and you take the output of it and you run it through any other function, as long as that function doesn't touch your data again, you maintain your privacy guarantee. So the composition is still differentially private. Okay, so this this post-processing function here doesn't touch my data again. It takes as input knowledge of my data. It doesn't actually touch the sample that was given. So I can use this to say that if I can analyze this mechanism here, then I get a privacy guarantee for the overall mechanism. Does that make sense? Good. Okay. So there are two parts to this proof then. So first is to establish this reduction. And the second is to analyze this simpler mechanism. So we're going to spend most of our time kind of discussing why the reduction works. I'm not going to go all the way through the proof, but we're going to kind of hopefully convince you that it's true. And then we'll briefly discuss how to analyze it, which is actually quite simple. Okay, so let's get into the reduction. So the first thing I want to do is look at what x1 and x1 prime are doing and establish that that is a reasonable thing for them to be doing. And I'm going to use this lemma from Kairu, O, and Viswanath, 2015. And what this lemma is, as you may have heard of it if you're familiar with differential privacy, basically says that any differentially private algorithm run on binary data is essentially just binary randomized response. And explicitly what it says is that if you have an epsilon differentially private mechanism from 0, 1 into any output space, then there exists a post-processing function B, and such that you can break down your mechanism as first running binary randomized response, and then doing some function on the output. Okay, so you can break it down in this way. So how does this help us? So we have A as our function from our data universe to Y. And now for this theorem, it's not important that these are actually 0, 1. So let's just relabel them. So we're going to relabel them in the first part of the mechanism by x1 and x1. And in the second part, the middle of our mechanism by 1 and 1 prime, the symbols we're using up here. Okay. So now we have this. And what is a mechanism from a binary function, from binary data into any data set? It's something more than just two distributions saying if your input is 1, sample from Q1, and if your input is 1 prime, you should sample from Q1 prime. Okay. So we have that just on x1 and x1 prime, A can be broken down like this as binary randomized response, and then sampling. Oh,
sorry, can I ask everyone to mute themselves? We seem to have some issues here, some static.
I think I have muting power, so.
Perfect. Okay, perfect.
Okay. But feel free to put your hand up, unmute, ask questions in the chat. I don't mean to like stop you from asking questions with my apparent muting power. Okay, so now let's look back at my mechanism up here in the corner and what x1 is doing. So essentially it's doing this. It's running binary randomized response. And now what we're saying is that I can send this 1 and 1 prime to the shuffler, shuffle it, send it to the central server. And then to get back a copy of A of x1 or A of x1 prime, all I need to do is tell the central server that whenever you see a 1, you should sample from Q1. And whenever you see a 1 prime, you should sample from Q1 prime. Okay. So this breakdown allows me to do this. So I can just send this 1 and 1 prime to the central server, and that's going to become part of my post-processing. Okay. So I've established that x1 and x1 prime are doing something reasonable. So now let's look at what everyone else is doing. So everyone else is going to do the same thing. So I'm just going to look at what x2 is doing, just so I have some notation to carry around. All right. So I'm going to use a different property of differentially private mechanisms. So here I have my PDFs, my probability density functions, of the distribution of A of x1 and A of x2. Okay, and these should be epsilon indistinguishable. And what epsilon indistinguishable really means is that if I multiply A of x1 by e to the negative epsilon naught, then it lies entirely below A of x2. This is exactly what the guarantee means. So what this means is I can write A of x2 as e to the negative epsilon A of x1 plus some other stuff. And I can normalize this other stuff and say that it is A of x2 is a mixture of A of x1 and something else with these mixture components. Okay. All right, so I have A of x2 decomposed like this now. I can do the same decomposition with x1 prime because A of x2 and A of x1 prime, of course, are also epsilon indistinguishable. And now I can write the average of these two things and say A of x2 does the same thing of A of x1 as A of x1 sometimes, does the same thing as A of x1 prime sometimes, and sometimes it does its own thing. Okay? And the amount of time that does its own thing is just 1 minus e to the negative epsilon. Okay, so these mixture components, if we look back up at our algorithm in the corner, these are the same mixture coordinates that I have in my mechanism up here. So e to the negative epsilon over 2, e to the negative epsilon naught over 2, and 1 minus e to the negative epsilon naught. But remember here, 1 and 1 prime didn't mean sample from A of x1 and A of x1 prime. It meant sample from Q1 and Q1 prime. So we established this connection before between sampling from A1, A of x1, and Q1 and Q1 prime. But that's fine. So these two mechanisms are symmetric. And so I can actually do this. I can say the same bound holds if I replace A of x1 with Q1 and A of x1 prime with Q1 prime. Okay, so now I have something that does look right. So I have the right mixture components. And what I can say is, if we look up in the corner again, if you see a 1, then you should sample from Q1. If you see a 1 prime, you should sample from Q of 1 prime. And if you see a zeta, you should sample from this leftover distribution. Okay. And so for 1 and 1 prime, this is fine to go through the server, to go through the shuffler and onto the central server. So whenever we see a 1, we sample from Q1. Whenever we see a 1 prime, we sample from Q1 prime. But this zeta, when I see a zeta on the central server, I don't know who it came from. I don't know if it came from x2, x3, where it came from. Okay, so what I need to do is make sure that that is fine, or why that is fine. And the reason that is okay is that all of the data points, except for the first one, are doing the same thing. So they're all sampling zeta with the same probability, and they're all going through the same shuffling process. So whenever I see a zeta on the central server, it's equally likely to have come from any of the data points, x2 to xn. So I'm just going to take all of the zetas that I see in the central server, and I'm going to randomly assign them to a data point. Okay, so once I randomly assign them to a data point, then I can sample from the leftover distribution of that data point. Does that make sense? Great. Okay, so hopefully I've now convinced you that this mechanism is doing something reasonable, and that on the server, all you have to do is convert these 1s, 1 primes, and zetas into samples from Q1, Q1 prime, and these leftover distributions. Okay, so because I expanded this out a little bit more here. So this is what x2 is doing. Okay. So now we have this reduction, or we've at least kind of convinced ourselves that this reduction exists. And so we need to analyze this simpler mechanism. So first, let's talk about why this mechanism should have higher privacy than epsilon naught. So notice that if I just look at the output of x1, so if the input is x1, it's slightly more likely to be a 1 than a 1 prime. And if the input is x1 prime, then it's slightly more likely a 1 prime than a 1. But slightly more likely only means by a factor of kind of e to the epsilon naught. So where our amplification comes from is that all of the other data points can also pretend to be ones and one primes. So they all, with some probability, pretend to be one or pretend to be one prime. So I can sort of imagine this output to the first data point as sort of hiding among the cloud, hiding among the crowd. So I'm creating all of these kind of fake one and one primes that cloud which one was actually coming from this first data point. And so they kind of cloud the difference between the one and one prime to this first data point. So that's sort of the intuition of why this amplifies privacy. We're sort of creating a bunch of fake data points. Okay, I'm not going to actually do the analysis of this, but some idea of how one does it. So notice that after you shuffle, so once all of this data has gone through the shuffler, the only information that remains is the number of ones, the number of one primes, and the number of zetas. Okay, so all I need to do is keep track of those things and compute the distribution of those given inputs P and P prime and the indistinguishability divergence between them. Okay, so notice if I ignore x1, then the distribution of ones, one primes, and zetas is just a multinomial. And when I introduce x1 back into my distribution, I get that the output on the central server is kind of a mixture of shifted multinomials. And that sounds a little bit complicated, but it's really not. These are actually very computable things. So you can create a theoretical bound for them. But actually, if you want to get really tight bounds, then you can do this empirically. So for small n, we can actually just compute the probability density function of what the central server sees, these number of ones, number of one primes, and number of zetas. You can compute that PDF exactly for small n, and then just compute the divergence between what you get for P and P prime. For larger n, that becomes computationally infeasible, but actually with a few little tricks, you can basically compute that thing again. Okay, and that gives you a much tighter bound than the theoretical bounds do, and is much substantially better in practice. Okay, so I'm going to move on from our proof now. Any lingering questions about shuffling before I move on? Great. Okay.
I have a quick question. So this model here works also for non-binary outputs?
Yeah. So the reduction that we used doesn't depend on being binary at all. So the very first, or one of the first papers really relied on binary. And you can actually get tighter privacy guarantees for binary if your input data is binary. But nothing we've said so far has relied on that.
Okay.
Yeah. Okay. So what I'm going to do now is do our little callback to stochastic gradient descent and see what this tells us about stochastic gradient descent. So again, I'm going to change my mechanism just a little bit. And so now I'm going to, instead of iterating over my data from 1 to n, I'm going to iterate over it in a random order. Okay, and this is the same as doing the output is the same as the output I would get from a shuffled mechanism. Okay, so I pick a random permutation, and at time step I look at x of pi as my step that goes into my gradient. Okay. So I still have the property that this is a local DP protocol. So each person is performing a epsilon 0 delta 0 local DP protocol, where epsilon is given by just this number, which again, we've seen a few times, comes from the Gaussian mechanism. Okay, and now I can directly use my shuffling amplification, because this really is a shuffling mechanism. A interactive one, but a shuffling one. Okay, so what my guarantee says is that I get epsilon delta dp, where epsilon is given by this formula here, and delta is a little worse than other deltas we've seen. So it's delta times either the epsilon times n. But remember that delta is supposed to be really, really tiny. and we typically don't pay very much for it in terms of our utility. So it's not a big deal that this is a little bigger than things we've seen before. But what is really important is this epsilon is small. Okay, so again, I'm going to focus on when epsilon naught is small, even though in general you do really care about larger epsilon naughts in the shuffle model. Okay, so when epsilon naught is small, we get a guarantee of about this thing here. Okay, and this should look kind of familiar. And if I plug in my bound for epsilon naught, I end up with log 1 over delta sigma square root n, which is the same thing that we got for subsampling. So if we go to our table, in the privacy guarantee, we have a little worse in delta, but the same thing in epsilon as we had for subsampling. We can release the noisy gradients, that's fine. We still can't release the order of the samples. So that's we have to kind of implement this shuffler, which is a little bit of a computationally hard thing to do. It's extra architecture for your system, but it really can be worth it for the square root. We've also gained something big from over subsampling. So firstly, we got back our local DP guarantees because we only interact with each person once. So we have local DP still. And also this is actually what happens in practice. So in practice, we do random permutations of the data over subsampling. And that is, for one, the local DP guarantee. Also because in many situations, it's kind of weird to go back to the same person and ask them the same question. So this permutation is just nicer in practice than subsampling. Okay, so this was privacy amplification by shuffling. I'm going to move on in a minute. Any lingering questions about shuffle? The shuffle model, of course, is much more general than stochastic gradient descent, but it is a nice way to analyze stochastic gradient descent.
So we have a question by Mohammed. The question is, I was wondering what happens if we do shuffling after subsampling. Do they compose?
Yeah, they would compose. Well, I guess it's a little unclear what it means because so shuffling depends on you having these local DP guarantees. And if I subsample, it's not clear what I mean to have a local DP guarantee to subsample a local randomizer. So I think you could probably get something out of it, but it's not clear that it would necessarily help you and that you would get kind of double the amplification.
Thank you.
Okay, so that was shuffling. So the final privacy amplification I want to talk about is amplification by diffusion, or just generally post-processing. I'm calling it diffusion because it tends to happen by adding Gaussian noise. But more generally, it's just post-processing. Okay, so suppose you have an epsilon differentially private mechanism A, and you take the output of it, and you run a post-processing function f, so f never touches your data again. And what we want to know is how much more private can the composition of these two functions be? So as I mentioned before, one of the kind of fundamental tenets of differential privacy is that post-processing doesn't degrade privacy. So this composition is necessarily just as private as the output of A was. So the question really is, when does it improve privacy? And so there are situations where it can and situations where it doesn't. So examples on the extreme, if f is a constant function that ignores the input, then obviously it produces a zero differentially private mechanism. And if f is the identity, then it doesn't do anything. It doesn't improve your privacy implication at all. So I want to point you to two nice papers on this topic that try and kind of characterize what differentially private mechanisms and what type of post-processing do actually improve amplification and how you might analyze this type of algorithm. So I highly recommend this Balabath, Gabordi, and Gumlik paper. But what we're actually going to focus on is this privacy amplification by iteration paper. Okay, so this can help us analyze SGD, which is why we're focusing on this one. And what it does is it looks at a very specific type of post-processing. So imagine this X0 is my person's data. So we have Alice here again with her data. And her data is going to go through a bunch of steps. And each of these steps has a very specific form. So I have a contractive map. So a contractive map is just a map that reduces distances. So you might also know it as a one Lipschitz map. And what's going to happen to Alice's data is at every step, it's going to be fed into a contractive mapping, and then Gaussian noise is going to be added to it. Okay. And the question is, after it's gone through T steps of this process, how much more private is it? And this seems quite niche, but this is actually, we're going to see the type of post-processing that happens in stochastic gradient descent. All right, so let's look at first our naive analysis of this. So I'm going to let my data universe be the set of all points that are in the 2-norm ball of radius 1. And so what that buys me is that I can say that just adding, running through a contractive map and adding Gaussian noise is necessarily just from the Gaussian mechanism, epsilon delta dp, with this epsilon delta that is now, I can't point to it, but on the line between x0 and x1. Okay, so my naive analysis would say, okay, so the first step is that private, and the rest of it is just post-processing, so it can't reduce my privacy. So I just get my final privacy guarantee being this. And so what Feldman, Mironov, Talwar, and Thakurta proved is that actually the composition is much more private. So if I undergo T steps of this process, then I get to divide my privacy guarantee by about square root T. So this is quite a lot. And I want to point out, just credit to the authors, this is actually a simplified version of their proof. Their proof is actually not stated in terms of epsilon delta dp, it's stated in terms of something called Renyi differential privacy, which is very similar, except that you replace the indistinguishability condition with the condition that the Renyi divergence between the random variables has to be small. And Renyi differential privacy has lots of nice properties. In particular, it composes a little better. So this is a slightly stronger proof. This is a slightly stronger statement in their paper than what I've presented here. Okay. So let's talk a little bit about the proof here. So the actual proof of this statement is quite complicated. So I'm going to give kind of something that might make you believe that it's true without actually going into the weeds of the proof. So suppose that my contractive map is the identity for all of my all steps. Then all that's happening is that at each step, I'm just adding Gaussian noise. So I'm taking x0, and by the time I get to xt, I've added t copies of Gaussian noise to it. And we know that when we sum t Gaussian noise distributions together, I just get one Gaussian noise with higher standard deviation. So the standard deviation is now square root t higher. Okay, now I just know, so if I have the property that my data points are 2-norm bounded, then I can say that A is epsilon delta dp for a smaller epsilon now. So now I've beefed up my standard deviation by square root t. So I get to put that in my denominator here. Okay, so the privacy of this map is much larger than of the original one. Okay, so the crux of the proof really is showing that these contractions don't make it worse. The identity is kind of the worst case, and that is a highly non-trivial proof. So it goes via Renyi differential privacy, or is stated in terms of Renyi differential privacy. It involves some really clever tricks. If you are interested in it, I recommend watching a video by one of the authors, Kunal Talwar, from a workshop from 2018 that is online. Yeah.
So Audra, just a question here. What type of post-processing is this? So this is a reduction to a smaller domain necessarily? Or...
So not necessarily reduction. So we're actually going to see an example of it in stochastic gradient descent. So it does seem at the moment maybe a little bit contrived, but these contractions can be any anything. And in fact, taking gradients is actually a contraction. So in stochastic gradient descent, we're going to see the step where you take the gradient is a contractive map, and then adding Gaussian noise.
But do you have restrictions on the structure of those contractive maps?
No. Any contractive map is fine.
Okay. Okay. Interesting.
Yeah, just one Lipschitz is important. I think so. I stated this in terms of it had to be contractive in like the 2 norm. I think they actually also have results that it can be contractive in like other norms.
Okay, I see. Thank you.
Yeah, so it's pretty general, kind of specific structure, but general within that structure.
It's very interesting.
Yeah, it's a really nice paper, and it's a really nice proof if you have time. Okay, so that was privacy amplification by iteration, which is kind of the idea that if you keep adding kind of Gaussian noise and doing more things, the data point is eventually going to forget where it came from. Sort of the intuition here. Okay, so let's look at how this helps us with stochastic gradient descent. All right, so these WIs are the iterates we had from stochastic gradient descent for each step. And what I'm going to look at is the view of a single data point. So let's say Alice's data, and Alice is person I. So her data gets mapped to W1, and then mapped to W1 prime, et cetera, et cetera. So it goes through a bunch of these gradient plus noise steps. Okay, and something I'm going to state but not prove is that these gradient descent steps are actually contractive. So this is falling into exactly this category we had for the privacy amplification by iteration. So what this means is that if Alice is the ith person who's for their data to be iterated over, she gets a privacy guarantee of square root log 1 of a delta over sigma times the square root of the number of steps that are left. So if she is the first person to go, this is going to be square root n, because there are n more steps to go. If she's the last person to go, then she's not going to get any amplification at all. Okay? So this is sort of an individual notion of privacy, which is not at all the notion of privacy that we are generally interested in. So if we were to naively look at this and try and bound the privacy of stochastic gradient descent, then we would have to take the privacy of the worst person received. So the worst privacy received by anyone in the data set, which would be the last person, that would be no amplification at all. So Feldman and all go a little bit further, and they say that we want everyone to have to pay the average privacy loss. So the privacy loss of kind of the average person in this set. And they can say they can achieve that by doing random stopping. So what this random stopping means is you pick a number between 0 and n, and you only run iterates until that number, and that number has to remain secret, but you can release the final point, and everyone gets the average privacy loss. Okay, so everyone gets a privacy guarantee of square root log n, square root log 1 over delta over sigma square root n. Okay, so I get a central privacy guarantee of this here. Okay, so if I look back at my table, this is a little bit worse than what I got for shuffling and subsampling. I have this extra square root log n, but it's a little better in delta. So the difference is sort of coming out in the wash, quite similar analyses. But I have some other differences here. So the first one is that I'm not allowed to release the noisy gradients anymore. So part of my privacy guarantee of this random stopping and the privacy amplification by iteration was you couldn't release any intermediate steps there. You could only release the final iterate. Okay, so I can't release my noisy gradients anymore, which is a bit of a blow. So they're useful for other things. But I can release the order of the samples that I interacted with, although I can't release my stopping time. So I do actually alter my mechanism a little bit, and I do this random stopping. And I mentioned earlier that not being able to release the gradients actually impacted your utility because the final iterate doesn't have particularly good utility guarantees. But actually, this random stopping gets by this because you end up, instead of averaging over the last lot of iterates, you kind of land at a random one. And so your average utility of a random stopping point is still quite high. So you don't really suffer in utility here. But if you wanted to use these noisy gradients for anything else, say computing how likely you are to be near the minimum, then you don't have them for that. Okay, so this is our final analysis of stochastic gradient descent. And so what have we learned? So we looked at 3 different privacy amplification analyses and guarantees that we got different guarantees for them. So whenever we implemented a new kind of system here, we got a much better privacy guarantee. It was about the same for all of them, but they all had kind of different pros and cons in terms of either needed to build a more complicated system architecture or not releasing intermediate steps of your algorithm. Okay, so just a quick review of the types of privacy amplification we looked at. The first one was subsampling. So if you only take a subsample of your data, then you can amplify your privacy that way. Our second one was shuffling. If you build in a shuffler between your data subjects and your central server, then you can get better privacy amplification, better privacy guarantees than the local model. And our last one was privacy amplification by iteration. So if you take your data and send it through many post-processing steps of a particular form, then you get better privacy amplification, better privacy this way as well. Okay, so hopefully this gave you some idea about some tips and tricks of how differentially private algorithms are analyzed. In particular, we use stochastic gradient descent, but all of these mechanisms and amplification results are more general than stochastic gradient descent. But it gave us a good backdrop for what you might want to consider when you're designing a privacy model for your system. Okay, so I'll end there. Questions, welcome.
Thank you, Audra. This was a fantastic tutorial. I think we all learn a lot from it. So I'm gonna open the audience for questions, the floor for questions. So you can either write your question in the chat or you can raise your hand. We did have several questions during your tutorial, so that was great actually to have this type of interactive tutorial. So I have a quick question. Meanwhile, maybe the audience warms up. So do you refer to all those different forms of amplification, privacy amplification, and also that more or less they achieve the same bounds, but do you have any differences in practice, or better, can you provide any guidelines for practitioners on when to use one type of amplification over another?
Yeah, so I think that probably the strongest one is shuffling. So the iteration one is very specific to types of algorithms, and shuffling is very general. So it always amplifies privacy for local DP, and allows you to get both local DP guarantees and central DP guarantees. And if you have enough people in your system, then you're really getting very good shuffling guarantees. And the local guarantees can kind of be a backdrop. There is a cost to implementing a shuffler. So it could be implemented in a couple of different ways. One of the common ways is to have kind of on 2 servers to do sort of a multi-party thing, but you have to not own both of the servers, hopefully, and limit, or at least limit contact between them, believably have a distinction. I think mixed nets are also a way of doing it. So there is some computational overhead, but if you can do that, then it offers more benefits, I would say, than subsampling. If your goal is privacy amplification, obviously subsampling occurs naturally a lot of the time. So I know people are studying subsampling in survey statistics where it kind of naturally happens. But if you want to build one of these into your system, then I think shuffling is probably the way to go. It's very, very general and has a lot of benefits.
Okay, thank you. So any question from the audience? And I would assume that they would also work with some sort of hierarchical shufflers, right? So you don't necessarily have to have a single server that takes in all the data and waits essentially for all the contributors bringing in the data and start shuffling. But
right, yeah. So it's a really important, a really important comment that the shuffler doesn't have to like collect all the local reports and then shuffle them. It can send them kind of as they come into the central server, just as long as the central server doesn't know who they're coming from.
Right.
So as long as you can maintain that anonymity, it's not important that it happens kind of all at once.
Yes. And any comments on the fact, so especially the first method, so the privacy amplification by subsampling, I think you rely on this subtlety on the choice of the random seed, which might be a little it may compromise the whole use of the algorithm if there is release essentially. So any comment on that, especially when we are deploying off-the-shelf algorithm that typically rely on some initialization that is already given?
Yes, the question is if you don't have perfect randomness.
Sensitive. Yeah, so essentially if the pseudo randomness of the algorithm plays an important role here.
Yeah, so I haven't really thought about that, to be honest. But I think that it would certainly. So nothing we said obviously goes through to me if you don't have true randomness. I think there are probably still some nice things you can say. But yeah, I think you wouldn't. So like this is generally true in differentially private algorithms that if you don't have true randomness, then like if you have like pseudo randomness that is only computational, then you don't get true differential privacy. And I think you could probably say something, you would probably have a similar effect here.
So we have one question from Borja. So the question is, does the shuffling have any effect on the utility? The question continues says that it seems to me that this is something we already do in normal stochastic gradient descent. So it appears to me that the utility should be the same as SGD plus Gaussian mechanism, but we can assert that it has better privacy guarantees.
Yeah, so that's a really great point. So shuffling in kind of itself obviously doesn't impact utility, and you're right that I think the motivation for the original shuffling paper was that this actually happened. This is what people do in practice. They were already anonymizing. But what it does give you is better privacy guarantees give you better utility, because typically what you want to do in your system is you have a target privacy guarantee. So you've got an approval for like 1 epsilon differentially private, a 1 epsilon differentially private mechanism, and you need to design your mechanism to achieve the privacy guarantee that's your target. And so when you have a better privacy analysis, what that means is that you can set, in this case, your sigma to be smaller in order to achieve that privacy guarantee, which improves your utility. So they're kind of two sides of the same coin.
Perfect. Well, okay. Yes. So just a comment. Amazing results. Well, that's. I think if there is no other question from the audience, so let's thank Audra once more. So thank you, Audra.
Thanks for coming, everyone. Yeah, it was great to be here. I'm happy to chat if anyone wants to talk about anything that I talked about.
Perfect. Thank you so much. And so the workshop will take a break right now. So we're going to see everyone back at 1:30 p.m. So this is Eastern time. And so we're going to start with the next session, which will include 3 spotlight talks.
Great.
Okay. See you in a bit, everyone.